What do the space shuttle, guns, mines that maim and kill, and the airbag in my car all have in common? They all involve rapid chemical reactions. Explosives, this time on Science Without Walls. Our nation and our population have developed various chemical addictions. We are addicted to chemical reactions, driven by entropy, which produce high temperatures and pressures to launch bullets from guns. We have the largest per capita ownership of guns of any nation on earth. The very wide availability of guns, particularly handguns, and their indiscriminate use for unlawful and inappropriate purposes have led to a growing tension and sense of insecurity in our nation. We have the highest per capita number of gun-inflicted injuries and deaths of any nation on earth. Chemical reactions are driven by entropy, the increase in entropy of the overall system. The most highly entropic state of matter is gas, and the most highly entropic form of energy is heat. Imagine a chemical reaction in which very large quantities of gas and of heat are formed in a very small enclosed volume in a very short period of time. That is an explosion. Pressure results from large numbers of energetic gas molecules randomly colliding with surfaces and walls. The greater the energy, the temperature of those gas molecules, the greater their velocity, so the more collisions they make. The greater the number of gas molecules in a small confined volume, the greater their collision rate, and therefore the pressure. The properties of the gas in a confined volume are related to pressure, volume, and temperature. Keep the volume constant and increase the temperature, the pressure increases. At higher temperatures, gas molecules have more energy, greater velocities, so they collide with the walls more often, so the pressure is greater. Decrease the volume with the temperature constant, the pressure goes up because the gas molecules have less room to move, and so they collide with the walls of the container more often. These relationships are summarized in the gas law. Pressure times volume is proportional to temperature. We can also say that pressure is proportional to temperature divided by volume, or volume is proportional to temperature divided by pressure. They all say the same thing. Now imagine I have a hydrocarbon which I can burn, combust, react with oxygen to produce heat and gases, water and carbon dioxide. We'll provide the activation energy for this reaction by a spark, igniting the combustion. The heat from that combustion continues to drive the process, producing more and more heat and more gases of combustion. That all occurs in a small volume inside the cylinder of your automobile engine. The gas molecules become very energetic, producing enormous pressures, pushing the piston. Your auto engine's volume is quite large. Cars have 4, 6, 8 or more pistons, cylinders, with a total volume ranging from 1.5 to 6 liters or so. The coupled motion of these pistons produces rotational velocities of up to 5,000 revolutions per minute, RPMs, or up to 100 revolutions per second. The pressures generated in your car are really pretty wimpy as far as explosions go. It is a controlled, low pressure, low temperature explosion. Now, imagine a fuel in which the oxygen is built right into the fuel molecule itself. So we don't have to deliver oxygen to the fuel. It doesn't have to diffuse or move in. The fuel doesn't have to burn from the surface inwards because the oxygen is already inside the fuel. Imagine that such a fuel is a solid or a liquid, and as it internally combusts or rearranges, It produces gases and heat. A good example is nitroglycerin. Take a very simple, common biochemical, glycerin or glycerol, which is just propane in which one hydrogen on each carbon has been replaced with a hydroxyl group. We call it trihydroxypropane or glycerol. Now figure out a way to react glycerol with nitrates, such as nitric acid. Nitrates are fascinating compounds. It turns out that nitrogen can bind to 3 oxygen atoms, sharing its 5 electrons with the 6 electrons of the 3 oxygens, in such a way as to form a tight, stable grouping called nitrate, NO3. Because oxygen brings 6 electrons to this partnership and nitrogen brings 5, the nitrate group has, overall, an excess electron, providing it with a negative charge. It binds potassium ion, forming potassium nitrate, KNO3. The nitrate can also associate with a proton to form HNO3, nitric acid, one of our most powerful oxidizing acids. And nitric acid will react with glycerol to form nitroglycerin. A nitric acid proton reacts with the glycerin hydroxyl to form water, thereby replacing that hydroxyl with a nitrate. The result is glycerin trinitrate, commonly called nitroglycerin. You know from various war, spy, and terrorist movies that nitroglycerin is a very unstable compound, and if disturbed, can detonate with enormous release of energy. John Wayne is very careful with it in the film Rooster Cogburn. The nitration of almost any organic substance with very high degrees or levels of nitration can yield an explosive. Nitrate compounds are inherently unstable. They are the basis of many of our most common explosives. TNT, or trinitrotoluene, is another example. Even cellulose fiber can be easily nitrated, forming nitrocellulose, which used to be called gun cotton because of its wide use in early guns and explosives. It turns out that cellulose itself is very difficult to solubilize because its polymer chains hydrogen bond to each other very strongly in a highly ordered fashion, making it very difficult to induce them to come apart in solution. But it turns out it's easy to nitrate cellulose, and the nitrated version, nitrocellulose, is soluble in many solvents and solvent mixtures, and can even be made to form smooth, transparent sheets. In fact, in the early days of plastics, nitrocellulose was a widely used plastic called celluloid. Very old movie films were made on a nitrocellulose base, and as a result, were very highly flammable. The popular Italian film Cinema Paradiso shows the effect dramatically. In nitrocellulose, just as in nitroglycerin, the carbon part, the fuel, is intimately mixed with oxygen and nitrogen. So under the right conditions, the carbon and oxygen combine, forming carbon monoxide and carbon dioxide. The nitrogen components form nitrogen gas. The hydrogens and oxygens get together to form water. A lot of other things happen as well. Practically everything that forms is a gas, thereby creating an enormous amount of entropy, which is what drives this process. Well, fortunately, this doesn't happen generally without some activation energy, usually provided by a primer, a fuse, a blasting cap. But just a spark, sometimes just a spark from static electricity, can trigger the explosion, making working with explosives a hazardous occupation. Every once in a while, you read of an explosive or munitions plant or facility accidentally destroying itself. Various stabilizers are added to help control such behavior. Nitrocellulose and nitroglycerin decompose almost entirely into gases, so they are called smokeless explosives or smokeless gunpowder. In the old days of guns, a black powder was used. This was really just a mixture of fine powdered charcoal, serving as the carbon or fuel source, potassium nitrate, serving as the oxidant or oxygen source, together with oxygen in the atmosphere, and some pure sulfur to help bind everything together. Black powder was a mixture of these various components, but each individual grain of powder had to rapidly burn. It really didn't work very well. Nitrocellulose and nitroglycerin have all of the components needed for the reaction built right into the molecule. It's a far more intimate association, which means that the reaction goes very quickly, explosively. The stuff used in guns for the launching of bullets is not a high explosive, and it's not a simple combustible fuel, but rather it's a combination of the two. The idea is to generate a large amount of gas and heat in a very small volume, generating a high pressure in a very short time. The confined chamber has only one way out, and that one way out is up the rifle or gun barrel, taking with it a small projectile, a bullet. The pressure generated below the bullet pushes it out until the bullet reaches the end of the gun barrel and is launched into space with a launch velocity. From then on, it's a projectile, subject to the law of gravity and to air resistance. The powders used in ammunition are called propellants, and they often consist of some combination of nitrocellulose with a little nitroglycerin. Depending on the bullet they are designed to launch. Our candle needed a match, an activation energy, to get the process going. In a gun, the activation energy is provided by the trigger, a spring-loaded mechanical device, which is essentially a hammer for smacking something called a primer. The primer is also a highly nitrated compound. The primer is seated at the bottom of the cartridge. When struck by the trigger hammer, it ignites, providing the activation energy to then ignite the powder, which then, within a millisecond or so, produces the high pressures and temperatures which launch the bullet. The whole thing is over in 2 or 3 thousandths of a second. The bullet is usually launched at speeds of 1,000 to 2,000 feet per second, faster than the speed of sound. Guns and explosives are a very convenient and effective way to integrate physics, chemistry, and biology. Firing a gun involves a chemical reaction, generating high temperatures and pressures, launching a projectile. That projectile obeys physical laws, basically Newton's laws of motion, and that projectile's ultimate purpose is to kill or wound a living organism. And that, of course, is biology, the science of living things. The bullet's function is to kill or wound the enemy in the case of war. It's to kill or wound some animal if you're a hunter. In the case of the use of guns in many parts of our society today, it's to intimidate or threaten, to use the threat of wounding or killing for some other purpose. Unfortunately, there's a fourth and rapidly growing unintended application of the very widespread distribution of firearms in our country. And that's the killing or wounding of the innocent, the uninvolved, or innocent bystander, caught in a crossfire. And of course, those innocents who are the victims of the accidental discharge of guns. There are also millions of other innocents throughout the world who are the victims of an insidious anonymous weapon called the landmine. Here the explosive charge, encased in a stable device, is initiated by local pressure, such as a person's weight. Landmines have been distributed by the millions around the world for the sole purpose of killing or maiming the local population, including our own peacekeepers. Unfortunately, explosives and propellants are relatively inexpensive, they're easy to manufacture, and with today's technology and knowledge, they are easy and safe to distribute and employ in weapons, whether they be grenades, mines, bullets, or other explosives. Weapons are purchased to be used. Although some guns are purchased by collectors and are to be appreciated essentially as works of art or as historical or cultural artifacts, the great majority of the guns purchased or otherwise distributed in this country are for offense or defense. They are not useful if they are completely locked up and inaccessible, so they tend to be available in the glove compartment, under the seat, under the pillow, in a purse or handbag. The tragedy and irony of personal gun ownership is that the odds are, the statistics show, that a gun in your home, in your car, or in your purse will likely be discharged or used inadvertently, accidentally, long before it is ever used for intentional defense or offense. Remember one basic principle, the normal distribution curve, the bell curve. It applies to everything in our natural world, and not just to the distribution of energy among molecules in a gas. Accidents happen. The more guns we have, the more gun-related accidents there are. The more cars we have, the more car-related accidents there are. And the more drugs we have, the more drug-related activities and incidents there are. Guns, cars, and drugs are not at all independent. They are often intimately and closely interrelated. Back to some bullet physics and bullet biology. A bullet loses velocity after it is launched due to air resistance. It must have some reasonable velocity, some kinetic energy, in order to inflict enough damage on the target to be effective. Its degree of effectiveness depends on how that remaining energy is dissipated when it contacts and enters its target. This is related to the concepts of range and firepower. Most biological tissues are relatively soft, containing nearly 70% water. Small, clean, smooth bullets can enter such gel-like structures without dissipating a lot of energy. They can make their way through and continue on out the other side. Bullets for target shooting are often of this type. Other kinds of bullets, however, are designed and built to dissipate much of their energy within the target, within the enemy or prey. A good example is so-called Varmint Bullets. When they encounter the resistance of entering a small animal, they expand and disintegrate internally, dissipating most of their energy within the organism, creating immense destruction with the obvious goal of death. The good news is that bullet doesn't continue through the victim to ricochet off rocks or other structures and go off in some other direction. The very bad news is that there are bullets now designed to be used on people, even those with bulletproof vests. These bullets are not intended to intimidate. They are not intended to wound. They are intended to obliterate. Bullets for hunting are a compromise. You don't want to totally obliterate the deer or other prey if you go hunting. For most hunters, part of the goal is to bring home some meat, and you don't want to simply wound or maim the deer and let it get away. And because the days of tracking and hunting skills have been largely superseded by advanced weapons technologies, you want that bullet to have its effect at a very large distance. We were able to obtain this watermelon simulation to let you see just how much destructive power common everyday guns and bullets deliver. Picture that watermelon as a rabbit, a deer, or even a man. It's obvious what destructive power these bullets have. They are intended to kill, to terminate a life. That is biology. Let's move from killing to the saving of lives. Let's talk about airbags. Many cars on the road today have at least one airbag. Airbags are to protect you from a very rapid deceleration, from an abrupt stop. Your car stops, you keep going. Since energy must be conserved, your kinetic energy must be absorbed, actually transformed, and preferably not by deforming and damaging your face and body. The airbag is there to help absorb and transform your kinetic energy. The bag must inflate in nearly milliseconds and then begin to deflate almost immediately, so you hit a soft rather than a hard or rigid bag. Let's focus here only on the chemistry. The gas which inflates the 70-liter bag is produced by a chemical reaction, a slow detonation, liberating nitrogen gas. Generally, sodium azide is electrically detonated to produce sodium and nitrogen. In a second but very rapid step, the sodium reacts with potassium nitrate to form even more gas. And finally, the potassium and sodium oxides interact with silica, SiO2, to form an inert glass. This last step is just a way of getting rid of the sodium and potassium oxides which form. The end result is that in milliseconds, enough nitrogen is produced to inflate and pressurize that 70-liter bag, allowing it to deform as you hit it, thereby absorbing your kinetic energy and protecting your face and body from undesired energy-absorbing deformation processes. So an airbag is a good example of a closed, controlled, entropy-driven explosion.
3, 2, 1.
There are many good and useful applications of explosives. They are safely used in mining, for excavation, for demolition of buildings, and to launch space shuttles, and to inflate auto airbags, protecting you and your passengers in accidents. But there is also the widespread use of bullets, mines, and other explosives for absolutely inhumane and abominable purposes. Those applications are destroying our society. They must be stopped. This program, Chemical Reactions in Action, concludes Part 3 of the course. We've worked through chemistry. We've learned about the matter, the stuff of our natural world, from the basic elements and periodic table, including your personal periodic table, to atomic and molecular orbitals. We've learned about bonding, water, solutions and pH, the materials and chemicals in the home, molecular alchemy, chemical reactions, and now explosive reactions. But just as with physics, there's so much more. You really should take a chemistry course. With your physics skills, that's the rules of the universe, and now your chemistry skills, the stuff of the universe, we're ready to move to biology, the science of life. We'll see you next time in the real world.